So in the last class, we were talking about how to find out the shear capacity of web. Right? We have checked down whether it is safe or not. Right? So in today's class, in continuation to the seventh step, that is check for shear capacity of the web, we'll be doing check for shear buckling capacity of web, or check for shear buckling of web. So in order to find out the shear buckling capacity of web, we have two methods. Okay, the first method is the simple post critical method, and the second method is the tension field coefficient method. Since in the question they haven't specified which method you have to use exactly, what you're going to do is you're going to use the simple post critical method for the convenience purpose, because it gives the better results and also it is the simplest way of solving. So keeping in mind of the simplest way of solving, we are going to use the simple post critical method in order to check the shear buckling capacity of web. Okay, so that's how I am using the simple post critical method. So let's write that statement using simple post critical method. Okay, so what what you're going to find out is you're going to find out the elastic critical shear stress, then the slenderness ratio of the web, then the tau b value, then VCR value. So all these things will be finding out. Okay, so initially let's find out the value of elastic critical shear stress. Elastic critical shear stress. So how do you find out this elastic critical shear stress? You know the formula, that is tau CRE. Tau represents shear stress, CR represents critical, and E represents elastic. So elastic critical shear stress formula is kV into pi square into E divided by 12 into 1 minus nu square, where nu is the Poisson's ratio, times of d by tw whole square. Okay, so this formula is there in clause 8.4.4.4. If you want, you can refer this clause. Okay, so 8.4.4.4 clause talks about the simple post critical method. All the formulae related to simple post critical method are available in this respective section. Now here you need to know the values of kV. Okay, nu, which is the Poisson's ratio, Young's modulus of steel, which is capital E, D, and TW. So first let's write the Poisson's ratio value, which is always 0.3. And here the Young's modulus of steel is fixed, which is 2 into 10 power 5 newtons per mm square, or megapascals. So this is the Young's modulus of steel. So now you need to find out the value of kV. So if you refer clause 8.4.4, they have very clearly mentioned the values of kV as 3 categories. Okay, since in our problem we are not going to use the intermediate transverse stiffness. Okay, so since we are not going to use the intermediate transverse stiffness, the value of kV equals to 5.35. Okay, or you can write it is used when end bearing stiffness are used. So since end bearing stiffness are used, I have been telling you since the beginning of the problem that we are not going to use the intermediate transverse stiffness for the design of this problem, because they haven't said anything about whether you have to use intermediate transverse stiffness or not, right? So and they have also mentioned in the question that you have to use the thick web. So when you are using thick web, you don't need to provide the intermediate transverse stiffness. So when intermediate transverse stiffness are not being provided, the value of kV is taken as 5.35. Okay, so therefore tau CRE equals to the value of kV is 5.35 into pi square into 2 into 10 power 5, which is the Young's modulus of steel, upon 12 into 1 minus nu square, which is 0.3, that is the value of Poisson's ratio, and d by tw. where D is the depth of the web, which is 1400, and TW is the thickness of the web, which is 12 whole square. Okay, so if you solve for this one, you'll be getting the elastic critical shear stress as 71.04 newtons per mm square. Okay, so from this, you are going to find out the value of slenderness ratio of web, which is lambda W. So if you refer clause 8.4.4, you'll get this formula. So from the clause, the value of lambda W, that is slenderness ratio in web, is, just a minute, sorry. Yeah, so it is Fy upon root 3 into tau CRE. This is the formula to find out the slenderness ratio in web. Okay, so let's solve the values. You know all the values. The value of Fy is 250 by root 3 times of tau CRE, which is 71.04, which you have calculated just now. So this value will be corresponding to 1.425. And remember, the value of lambda W should not, should be greater than 1.2. Okay, so the value of lambda W should be greater than 1.2. When the value of lambda W is greater than 1.2, the value of tau B is calculated by using the formula, that is Fy upon root 3 into lambda W square. So this is the formula to find out tau B when you have the lambda W value greater than 1.2. So you know the value of Fy, which is 250 upon root 3 times of lambda W is 1.425. And this will be the value which is equals to 71 point, sorry, some, yeah. This will be the value which you are getting it as 71.08 newtons per mm square. Okay, so from this, you are going to find out the final value, that is a VCR, where VCR equals to, the formula is area of a web, that is AW. In code book, they will mention it as AV. AV or AW, they both are same, which is area of web times of tau B. Okay, so where area of web is calculated as depth of the web, that is 1400, times of thickness of the web, which is 12. Okay, into tau B value, that is 71.08. So which will be 1194 kilonewtons. Okay, so this is the value of VCR. And remember, this value must be greater than the value of the shear force, that is 996 kilonewtons. So if you check down the first step, okay, that is the design force step, you must know the maximum shear force value. Okay, the maximum shear force is obtained as 996 kilonewtons. So that's how this 996 kilonewtons has come from. So this 996 is the maximum shear force. So since the VCR value is greater than V, okay, since VCR is greater than V, it is safe. Okay, shear, the buckling of web under shear forces is safe. So it is considered as safe. Okay, so that's how you are going to find out the value of shear buckling capacity of the web by using simple post critical method. And in the next step, what you're going to find out is check for lateral torsional buckling. Check for lateral torsional buckling. So buckling of web actually. So you can limit this, or you can make it of web. Check for lateral torsional buckling of web. Now, how do you find out this lateral torsional buckling? First, you need to know whether this check is required or not. Okay, so first you have to identify whether the lateral torsional buckling check is required or not. How to identify? So it can be identified by looking at the question. So at what part of the question you can look and you can say whether this check is required or not. Suppose in the question, if you find anywhere this particular statement, that is laterally restrained. Okay, if you if you find anywhere in the question of this particular statement, the beam is laterally restrained or the girder is laterally restrained, then you don't need to do this check. So most of the times all the plate girders will be laterally restrained plate girders only. So 99.9% of the times when it comes to the exam point of view, you don't need to do this particular step, that is lateral torsional buckling step is not required for your case. Okay, so since, let's write that statement, since the beam is laterally restrained, since the beam is laterally restrained, so this is provided in the question. Okay, since the beam is laterally restrained, lateral torsional buckling of web, lateral torsional buckling of web is not required. Okay, so directly you can skip this step also, but if you want to mention, you can mention. Okay, however, you are not going to do this step. Anyways, so the next step, which is the additional step here, right? When you have the combination of the loads, this step is the additional step which you have to solve for. So which is design of load carrying stiffness. Design of load carrying stiffness. What are these load carrying stiffness and where exactly you're going to provide this load carrying stiffness? So usually the load carrying stiffness or the load carrying web stiffness should be provided. Okay, the load carrying web stiffness should be provided where compressive forces are through the flange. Okay, where compressive forces are through the flange by the action of loads or the reactions which exceeds FCDW. I'll repeat the statement in a word form so that you can write this statement. So you can make a note and then write on this particular statement. So where exactly you're going to provide the load carrying stiffness or load carrying web stiffness. So load carrying web stiffness, load carrying web stiffness should be provided. Please write this statement. Load carrying web stiffness should be provided where compressive forces, are applied through through flange by the action of loads or reaction forces, exceeds FCDW. Okay, so what is it saying is, you know the intensity of the factored load, right? You know the intensity of the factored load, which is 300 kilonewtons. Factored, yes, this one, factored concentrated load value, which is 300 kilonewtons. Now, what exactly this point is saying is, when the value of FCDW, okay, when the value of FCDW is less than the factored concentrated load or factored point load, okay, when FCDW value is less than factored point load, you don't have to provide the load carrying stiffness. Okay, that's what the above entire paragraph says. So when FCDW is less than the factored point load, only one point load, don't add 300 plus 300, it is only one point load. So when FCDW is less than factored point load, then the load carrying stiffness are not required. Okay, load carrying stiffness are not required. So let's check whether these load carrying stiffness are required or not. If it is required, then you have to design the load carrying stiffness. If it is not required, then you don't need to design. So you have to find out whether the FCDW value is less than the factored point load or greater than the factored point load. Okay, so if it is greater, then you don't need to provide the condition has to get satisfied. Okay, so if FCDW is greater than the factored point load, then the condition has to be satisfied. So let's check this point. So buckling strength of unstiffened web, okay, which is given by FCDW equals to, you have the formula, which is B1 plus N1 into TW into FCD. Okay, so this formula is available in clause 8.7.3 of IS 800/2007. Now here, when you have the combination of loads, the value of B1 is assumed as 0. Okay, this is an assumed value. When it is assumed as 0, when you have the combination of loads, that is UDL plus point load or UDL plus any other loads, then you can assume the value of B1 as 0. That's a straight away point. And then the value of N1 is calculated as 2 times of overall depth of the section, that is capital D, divided by 2. Okay, so that equals to 2 times of overall depth of the section. The capital D, that is overall depth of the section, equals to depth of the web plus thickness of the flange. Sorry, it is not web, it is flange. Thickness of the flange plus thickness of the flange. You have two thicknesses of the flanges, right? Bottom flange thickness and the top flange thickness. So the depth of the web, you have to, you know what is the depth of the web, that is 1400 mm, and the thickness of the flange is 40. Thickness of the other flange is also 40, which will be 1480 mm, right? 1480 mm. This is the overall depth. So that will be 1480 upon 2. Therefore, the value of N1 will become 1480. Okay, that is 1480 mm. Okay, so that's how you're going to find out the N1 value. Suppose, just assume in this way, this formula, that is the value of N1 equals to 2 into D by 2, N1 equals to 2 into D by 2 is used, that is 2 times of D by 2 formula is used when the load is getting dispersed at a 45-degree angle. Okay, when the load is getting dispersed at a 45-degree angle. So how you are saying whether the load is distributing at a 45-degree angle or not? You have to remember this statement, which is, always remember, whenever a point load is acting on the member, okay, whenever a point load is acting on the member, it will get distributed in this direction. I mean, in this way. This angle of distribution will be 45 degrees. So this is applicable for all the concentrated loads. So when you have the concentrated loads that are acting on the member, all the concentrated loads which are acting on the member will get distributed onto the next section by 45 degrees angle. So that's the key point here. So when you have the 45-degree load distribution, then the value of N1 will be 2 times of D by 2. So usually most of the point loads will be distributed in this angle only. Okay, so since we are designing the plate girder with point load, so I am assuming it as directly 45 degrees, and then I have taken this value of N1 as 2 times of D by 2. So that's how this value has come from. Okay, so now So the next statement is you need to find out the value of FCDW. So from this formula, you got to know the value of N1 and you also got to know the value of B1, right? Both N1 and B1 are found out. And you know the thickness of the web, which is 12 mm. Now you need to find out the FCD value, that is design compressive force. So how do you find out this design compressive force? So in order to find out the design compressive force, you need to know the slenderness ratio value, right? So let's come in a back way. So you need to find out the FCD value. So in order to find out the FCD value, you need to find out the value of lambda, that is KL by R, right? You know the formula, that is KL by R. In order to find out the value of R, you should find out the ratio, that is I by A. Okay. So then you also have to find out the value of KL. Right. This is the back pattern which you have to solve. And the value of KL is taken as 0.7 times of D, or that is depth of the web. So this is the pattern of how to follow or how to solve the value of FCD value. Right. So from again the table 9C of IS 800/2007, you know the built up sections belongs to buckling class C. So you have to use table 9C and then interpolate the value and then extract the value of FCD. So let us solve that. So first let me find out the value of KL. So KL equals to, I set the formula, that is 0.7 times the depth of the web. So that will be 0.7 times of depth of the web is 1400. Okay, so you can solve for that one. And then the value of R has to be found out, which is given by root I by A. Okay, that is the radius of gyration R equals to root I by A. So how would you find out the radius of gyration, I value, that is BD cube by 12. So it is taken as D, that is depth of the web, into thickness of the web cube divided by 12 whole divided by area of the web, whole divided by area of the web. How will you find out the area of the web? It is depth into thickness of the web. So from this you can find out the value of R, that is radius of gyration. Okay, and then you have to find out the value of lambda, which is slenderness ratio. Okay, so then the value of slenderness ratio is calculated as KL upon R. Okay, so you will get the value of KL here, and you will also get the value of R, that is radius of gyration. So once you solve those values, you will be getting the slenderness ratio as 283.5. Okay, you'll be getting the ratio of slenderness ratio as 283.5. If you want, you can solve. So you can take the value of D as 1400 and TW as 12, I think. So 12 cube divided by 12, that is 1400 into 12. So if you have to solve for this one, I did not solve. So since I am representing directly the value of lambda. Okay, you can solve and you can check down. So now you know the value of slenderness ratio, that is lambda. So since plate girders are built up sections, so they are all built up sections because you are using some additional members, that is you are using the end stiffness or end bearing stiffness. So since plate girders are built up sections, they belong to buckling class C. They belong to buckling class C. Okay, so when they belong to buckling class C, you have to use table 9C. So use table 9C of IS 800/2007. Okay, you have to use table 9C of IS 800/2007, and then you have to find out for lambda equals to 283.5, you have to find out the value of FCD. Okay, so when lambda equals to 283.5, you have to find out the value of FCD. But here comes the complication in this problem. What is that complication is? So I want everyone to open table 9C of IS 800/2007. So I'll share the code book as well. Just give me a minute. Before sharing, just remember the value of lambda, which is 283.5. Okay, the value of slenderness ratio is 283.5, and at that value you have to find out the FCD value. So yes, so this is table 9C. Now here, if you keenly observe, the values of KL by R are starting from 10, and with every 10-meter interval they ended up at 250. Okay, the last value of slenderness ratio is 250, but what is the slenderness ratio which you have obtained is 283.5. So for 283.5, you don't have the values of slenderness ratio. I mean, you don't have the values of FCD, right? So what you have to do is, instead of interpolation, you have to do extrapolation here. Okay, remember this thing. So when you don't have the values of a slenderness ratio in your code book, don't say that, don't think like you did somewhere wrong in the calculation of slenderness ratio. You must have done right, but the thing is, instead of interpolation, you have to do the extrapolation. Now the question is how to do extrapolation. So in order to do the extrapolation, what you have to do is, you have to take the values of FCD. Okay, very carefully you remember, you listen. In order to do the extrapolation, you have to take the values of FCD for the last two values of lambda. That is, yeah. So that is, you have to take the value of FCD when lambda equals to 240, and you have to take the value of FCD when lambda equals to 250. Okay, so for when lambda equals to 240, the value of FCD is 26.2, and the value of when lambda equals to 250, the value of FCD is 24.3. Please make clear here. So when you don't have the value of slenderness ratio in your code book, you have to do the extrapolation. Now, in order to do the extrapolation, what you have to consider is, you have to consider the values of FCD for the last two cases, that is for 250 and 240, right? So for 240 and 250, you have to take the FCD values, and then you have to do the interpolation, extrapolation. Okay, so let me teach you how to do the extrapolation terminology. So I'll stop the screen sharing. Yeah. So now we have to do the extrapolation. Okay, so by extrapolation, please remember why we are doing extrapolation, because the lambda values in the code book or in the table 9C are limited up to 250 only, right? Since you don't have the lambda of 283.5, you cannot find out the value of FCD. So since you cannot find out, what you're going to do is, you're going to do the extrapolation. What is this extrapolation and how to do this? So as I was telling earlier, you have to take the last two values. Okay, so you know for lambda equals to 240, FCD value is 26.2, and when lambda equals to 250, the value of FCD is 24.3. And remember, in both the cases, the value of Fi is 250. So this I'm not repeating, because you know already, right? Now, what you have to do here. So here, first thing is, you have to calculate the differences of these values. That is 240 and 250 difference is 10. Okay, forget about minus symbol, don't keep that one. So 250 minus 240 will give you 10. And then 26.2 minus 24.3 will give you 1.9. Okay, so the first thing is, you have to calculate the differences. Now, for lambda equals to 10, okay, for lambda equals to 10, what is the value of FCD? It is 1.9. Okay, for lambda equals to FCD, for lambda equals to 10, the value of FCD equals to 1.9. Just remember this value. Now, for what value of lambda you have to calculate the value of FCD? You have to calculate the value of FCD when lambda equals to 283.5. Okay, so now you have to subtract, okay, you have to subtract 283.5 with 240. Okay, the last but one value, not the last value, that is not the 250 value. You have to take the last but one value, that is 240. So therefore 240 equals to 240 minus 283.5. So at this value you have to find out the FCD value, and this difference will give you 43.5. Forget about the minus symbols, it is not required as of now. So the difference is 43.5. Now, so for lambda equals to 10, the value of FCD is 1.9. Okay, and for lambda equals to 43.5, you have to find out the value of FCD, which you can write it as X. Okay, so now after you do proper checking, the value of FCD, okay, the value of FCD at lambda equals to 43.5 is obtained as 8.265. You do the calculation and you can check. Therefore, the value, the final value of FCD, remember this is not the final value. Okay, so the final value of FCD is calculated as, okay, it is calculated as 26.2 minus 8.265. What is this 26.2? 26.2 is the value of FCD when lambda equals to 240. Okay, 26.2 is the value of FCD when lambda equals to 240. So finally, you're going to get the value of FCD. Okay, so can somebody tell what is the value of FCD here? It will be 17.26 minus 8 is 17.94. Yeah, 17.94 newtons per mm square. So this is the final value of FCD. So that's how you're going to do the extrapolation. Okay, I hope it is clear for all of you. So finally, you're going to find out the value of FCDW. So therefore, FCDW equals to B1, that is a formula where B1 equals to 0 and plus N1, okay, where N1 equals to 2 times of D by 2, which is 1480, into thickness of the web, which is 12, into FCD, which is 17.94. And this value is 318.6 kilonewtons. And remember, this value should be greater than the factored concentrated load, which is 300 kilonewtons. So if the value of FCD is greater than the factored concentrated load, it is termed as safe. That is, therefore, a web is safe against buckling. That means the web portion will not get buckled. Therefore, load carrying stiffness are not required. So that's how you're going to check whether the load carrying stiffness are required or not. That's the final point. So since load carrying stiffness are not required for our case, we are not going to worry about the design of the load carrying stiffness. Okay. Now, the 11th step. So which is, you can make it as 11th step, which is design of load bearing stiffness. So there is a difference between load carrying stiffness and the load bearing stiffness. I'll let you know where you are going to provide this load bearing stiffness. Just keep the heading as design of load bearing stiffness. What is this? So usually the bearing stiffness or the load bearing stiffness should be provided for webs. Okay, they should be provided for webs where forces are applied through flanges by loads or by reaction exceeds the local capacity of the web. I'll tell you. So you can write this statement. You can make it as note and write down. Note. These should be provided, or load bearing stiffness should be provided for webs where forces applied through a flange by loads or reaction forces or just reactions exceeds the local capacity of web. So you have to find out whether the forces are exceeding the local capacity of the web or not exceeding the local capacity of the web. So how will you find out this one? So in order to find out, you have to refer clause 8.7.4. Okay, if you refer clause 8.7.4, the value of FW, which is local capacity of the web or force in web. So the local cap, just a minute. Yeah, so local capacity of the web is generated with FW. So from this, if you refer clause 8.7.4, the value of FW is FB1 plus N2 into TW into Fy by gamma m0. So this is there in clause 8.7.4. You can refer this clause if you want. And here, when you have the combination of loads, again, when you have the combination of loads, the value of B1 is taken as 0. So it is just an assumption. So when you have a combination of loads, directly take the value of B1 as 0. And the value of N2, okay, it is taken as 2 times of, okay, 2 times of thickness of the web, okay, 2 times the thickness of the web times 25. Okay, so 2 times the thickness of the web times 25. So I'm just making it as 2 times of thickness of the web. Sorry, not the thickness of the web, it is the thickness of the flange. Sorry, it is the thickness of the flange, which is 40 into 25. So this will give you 200 mm. Okay, so therefore force in web FW equals to B1 value is 0 plus N2 value is 200 and the thickness of the web is 12. Fy value is 250 upon gamma m0 is 1.1. Okay, so this will be 545.45 kilonewtons. Okay, so you have solved the value of FW, right? Now you need to find out the whether load bearing stiffeners are required or not. So how will you find out? So in order to find out this one, you have to calculate 2 more points, which is load bearing stiffeners are required at, so usually the load bearing stiffeners are provided where there are the concentrated loads. Okay, remember, load bearing stiffeners are provided where there are the concentrated loads and also at supports. So I'll just write this point. So load bearing stiffeners are usually provided at 2 locations. One is where you have the point loads and the second thing is where you have the supports. So you have to find out whether the load bearing stiffeners are required exactly under the point load or exactly at the supports. So you have to find out this case. So I was telling that load bearing stiffeners are usually required at 2 locations. One is at exactly under the point load and the other one is at exactly at the supports. So for this, you have to find out where they are actually required for you. So fine. So the first thing is you have to find out at location of 300 kilonewtons point load. At the location of 300 kilonewtons load, because you have the point load intensity is 300 kilonewtons. So let's check that one. You know the value of FW, that is 545.45 kilonewtons. So you know the value of Fw, which is 545.45 kilonewtons. And remember, this Fw value is greater than the point load intensity, which is 300 kilonewtons. That is safe. So therefore, wherever the point loads are acting on the member, you don't need to provide the bearing stiffener or the load bearing stiffener. So therefore, load bearing stiffener, load bearing stiffener is not required, below the point load, below the point load. And again, you have the second case, which is at supports. So you also have to check whether the load carrying stiffeners or the load bearing stiffeners are required at supports or not. Now, how do you find this? So you know the support reaction, okay, which we have found out in the beginning steps. So the support reaction is 996 kilonewtons, which is the maximum shear force value. And you have to check this value with Fw. And the Fw value is 545.45 kilonewtons. And 545.45 kilonewtons is less than 996 kilonewtons. So it is unsafe actually. Okay. So therefore, load bearing stiffeners, are required at supports. So that's how you're going to identify whether the load bearing stiffeners are required or not. So you know, so from this connection, you know that wherever the point load is acting, you don't need to provide the load carrying stiffener. Wherever the supports are there, you have to provide the load bearing stiffeners. So now let's design the load bearing stiffeners at supports. Okay, so this point will be the 12th point. So design of bearing stiffener, at support, because you found out that the bearing stiffeners or the load bearing stiffeners are required only at supports, right? That's the reason why I'm solving only at supports. No. So usually you have to find out the dimensions of the supports, dimensions of the bearing stiffener. It is commonly taken as, usually the width of load bearing stiffener will range in between 200 to 220. Okay, this is width. And the thickness of the load bearing stiffener will be ranging in between 10 to 12 mm. Okay, so this is the typical, these are the typical values. So the width of load bearing stiffeners are usually ranging between 200 to 220 mm, and the thickness usually ranges between 10 to 12 mm. So however, you have to do the trial and error method before selecting the load bearing stiffeners. Okay, so first let me try a pair of 220 as the width of load bearing stiffener by 12 mm Indian standard flats. I'm just trying here. Remember, these are not the final values. So these are just the values which you have assumed as a trial one. Okay, so now let's find out whether the dimensions of the load bearing stiffeners which we have selected are safe or not. So let us find out that. So before finding that, you need to find out maximum outstand of stiffness. Maximum outstand of stiffness. How will you find out this maximum outstand value? So you can find out it as 20 times of thickness of the stiffener. TS represents thickness of the stiffener times of epsilon. Okay, so this formula is available in clause 8.7.1.2. Okay, where in your code book they must have represented the value of TS as TQ. Okay, TQ or TS, they both are same, which is the thickness of the stiffener. So that will be 20 into 12 into the epsilon value is 1. You know this. So this will be 240 mm. Okay. So how much you have provided? You have provided 220, right? So the maximum outstand is 240. That means it should not exceed 240 mm. So that means you have provided within the limits only. So since 220 is less than 240 mm, the width is safe. The width assumed is safe. Similarly, you have to do the another check, which is outstand at core portion. I'll let you know what is this outstand of core portion. Outstand of core portion. So what is this outstand of core portion is nothing but, suppose if the extension of the stiffener is coming beyond the width of the flange. Okay, if the extension of the stiffener is coming beyond the width of the flange, then you have to revise the dimensions of the stiffeners. So how will you do this? So this is also obtained from 14 times of thickness of the stiffener into epsilon. So this is also available in same clause, that is 8.7.1.2. You can refer that. So that will be 14 times of TS is thickness of the stiffener, which is 12 times of 1, which will give you 14 into 12 will be 168 mm. And here also, since 168 is less than, okay, 168 is less than 220 mm. 168 is less than 220 mm. You have to use 168 mm as outstand. So use 168 mm as outstanding length or outstand. So that's how you're going to check down the design of bearing stiffness. So if these two conditions are getting satisfied, that is this condition and this condition and this condition, if both are getting satisfied, then that means the width of the stiffener which you have adopted, that is 220 mm, is sufficient. Okay, remember both the conditions should get satisfied. So since both the conditions are getting satisfied, you can take the width of the stiffener as 220 mm. So thickness you can take either 10 mm or 12 mm. So mostly you go for a little higher amount of thicknesses because you are providing the stiffener exactly at support. So at support, you can expect high amounts of loads. When there are high amounts of loads, obviously the thicknesses or the dimensions of the member should be little greater. So that's the reason why I'm going for the upper value, that is 12 mm. Okay, so that's how you're going to design the bearing stiffener at support. Now the next step, which is the 13th step, is check for buckling of a bearing stiffener. So check for buckling of bearing stiffener at support. Okay, so you have to check for the buckling of bearing stiffener. So you have provided the stiffener now. Now what you have to do is you have to find out whether this stiffener which you have provided with the 220 by 12 mm dimension, whether it is buckled or not, whether it gets buckled or not. So you have to find out the buckling capacity of the bearing stiffener which you have provided at supports. So in order to find out that, you have to find out the buckling resistance. So how do you find out this buckling resistance is? Buckling resistance, that is FQ or FD or FQD, anything is fine. FQD equals to area into FCD. Now here you need to find out the value of FCD. In order to find out the value of FCD, you need to find out the slenderness ratio, the radius of gyration, I value, R value, and the effective area, right? So fine. So before finding that, let me draw the diagram to simplify the process. So this diagram is mandatory in your exam also. This is the web portion. Okay, I'm just drawing the web with stiffness. Okay, so this is the web portion. And the stiffness are also provided, right? These are the stiffness. You are providing the anyways. So the diagram goes in this way. You have the web portion, which is represented in green, and you also have the stiffness portion, which are represented in pink color. Okay. Fine. So this is the web portion. The green one is the web portion, and the vertical ones are the stiffness. Now here, the end bearing, the effective area has to be calculated for this one. So how do you calculate the effective area? Effective area equals to 2 times of outstand at core section, that is 168, because you have found out that outstand of the core section is 168. Okay, so 2 times of 168 into the thickness of the stiffener, which is 12 mm. You have found out this one. So 12 mm, not you have found out, you have assumed, plus, okay, plus 20 times of thickness of the web, okay, plus 20 times the thickness of the web. And you also have another condition, which is into the thickness of the web. It is happened. Anyways, so in order to find out the effective area, you are going to use this formula, that is 2 times of 168, where 168 is the outstand at core portion. Now, what is this outstand of the core portion? Okay, you have to identify this outstand of the core portion. So I'll draw this outstand of the core portion, which is